Hey guys, I wanted to give a quick status update. Major breakthrough. Last night I started work on an encoder for the Atari Educational System tapes, and as of just roughly 2 hours ago, I was able to successfully encode new data onto a new WAV file, which can be played back at the tape for the Atari Educational System. Now, before we actually get into the demo here, I'm going to take and give a quick little run through of the code. And then after I've done that, then I'll take and show this actually in action here. So for the purposes of this, I actually developed this on my Mac, and I've copied the code over here to the Windows machine so we could see it. And as we can see here, this is basically in plain C. And as of right now, it's outputting a raw audio file without any headers whatsoever, with a fixed sample rate of 44100. And this will actually, of course, be changed to output standard WAV files. It outputs a stereo file for now so that I can take and insert the voiceover tracks later. And the constants that we have here basically define the standards for the tape. Atari tapes are frequency shift keyed with mark and space tones of 5327 and 3995 hertz respectively. The critical aspect here is that the transmission rate is set up in the Atari Educational System for a 600 baud rate transmission. That means that the period size and the buffer sizes are absolutely critical to absolutely stay at this speed. When I initially did the encoding and was successful, it was actually outputting the text at very fast rate at a full 600 bits per second, which is actually a bit too fast to read. So I initially tried to take and extend this value here to double it to make the bits longer. However, this causes the encoding to fail completely. Don't do this at all. So what we wound up doing instead, I will actually show in just a moment. So we have a number of different functions here, which I'm going to take and pare down and refactor to be a bit cleaner, to do things like write the tape leader, which is basically just a series of mark tones. And of course, to write the individual baud rate bits that are the size of the buffer here. We subsequently go ahead and write the functions for write mark, write space, write the start bit, write the stop bit. And once we actually get down to write byte, then we actually start to do things rather interestingly. Now for this here, just ignore this. This was something I was testing. I'm going to go ahead and pull that out. But as we can see here, it's basically just a straight bit shifting operation. We take each bit in the byte, we shift it out, and we figure out whether it's set or not. If it's set, write a mark. If it's not, write a space. And before each set of data bits, we of course write a start bit, and after each set of data bits, we write a stop bit. Fairly standard, fairly straightforward. So, after that, we take and build a little bit on top of that for writing strings. Again, we just kind of traverse through and write each byte out. And there's a special function here called write pause. Now, if you had followed my earlier work here, you'll see that we noticed that the null byte here, byte 0, is actually used for timing purposes. Well, it's also used for pauses, and it has to be used as such here. So in this case, what I basically do, given the number of milliseconds that we want to take and pause, we calculate the number of nulls we'll need to take and fulfill that pause and just write them out. Now, the test part of the program here, we open up a raw file, we write a leader on it, and we basically have a series of strings here. Now, I'm still not entirely sure what's going on here. At the very top of the screen, sometimes depending on what's being written here, you won't see the first line of the screen. So I'm adding additional data in until I actually see the first line, and I will figure out what the deal here is. And as we can see here, in between little bits of text, I'm adding bits and pieces of pauses so that we can take and have a chance for the voiceover to catch up and to catch my breath. We write it out, we close it out, and what we wind up with is a raw file. that contains the data. Now, I do actually have a copy of Audacity on here, and I'll show you what winds up getting written after we go through, convert it to a WAV file, and add the voiceover to the other side of it here. Let's open a file. For this, I'm actually going to have to go, come on. My machine has decided to pause for a moment. Come on, quit it. Let me type in it, please. Actually, you know what? I will do this from a different standpoint right here. Apologies. Home, temp. And as we'll see here in a moment, as I was building this out and testing the encoder, there were many different attempts, and the attempt I'm actually going to wind up showing you is attempt number 16 here. Yeah. Shame on you for not allowing me to do that. We'll just take and put it here. Now, we'll actually go in, open up the file. No, don't make a copy of it, just read it. And we'll see here that the output of the file is actually quite clean here, especially the digital data in the second track. We're not particularly interested in the voiceover data, so I'll just go ahead and pull that away, but you can see that the voiceover data is in the left-hand side of the track, and the digital data is actually being stored on the right track. So we'll take and split this out for a moment. And now we actually have access to the actual data. Now the leaders are primarily made up of marks and spaces, and we'll take and zoom in real quick so you can see the quality of the waveform. It's a pretty standard sine wave function here. I had to make some adjustments thanks to Joey Z to get the harmonic distortion problems that I was having earlier out. But as you can see, it's a very, very clean sine wave. Come on. Marked in space. And as you actually go through, we'll actually pull through and you can see some of the marks and spaces in the waveform here. Bit, 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 bit. And it encodes quite nicely. I'll take and play a small snippet here. So as you can see, encodes beautifully. And so what does this give us at the end of the day? Let's find out. Now we can go look. We'll open up the Atari Educational System here, and we will insert a tape containing the WAV file that we just output. It bumps it in. It's about 15 seconds long, not that long, but just long enough to get the point across. And one thing I will show you here, as I've showed before, we have to make sure that load data as audio is selected so that the system will actually encode it and play everything together. But now that that's in place, we hit start. Hello everyone. This is a test to show data being streamed from a new tape, encoded with the EduEncode libraries being developed to make new tapes for the Atari Educational System. Hello to everyone at Atari Age. Thanks for all the encouragement. So there you go. Still more to be done. I have to figure out the different control codes for things like clearing the screen, selecting the right answer, doing the inverse highlighting functions. But there is now enough here that we can actually, we're actually seeing the light at the end of the tunnel. Once this is done, I will package this up as a library and make a simple tool, text base at first, to be able to take and create new educational system tapes to be able to synchronize both the voiceover and text for various different applications. So, and I will take and make a demonstration tape to show how this works. So there we go, guys. It's one hell of a status update, I think. enjoy. If you guys have any questions, feel free to hit me up on the forums. Thank you. Good night.